In the last video, we reviewed how to simplify a complex fraction. This is a continuation of that. So in this case, the question would normally say, simplify the complex fraction. So again, I'm going to head and write it down. So 3n over 1, since there's nothing underneath it, minus 1 over 3n, all divided by 9n squared. And I'm going to write again the 1, since there's nothing underneath, and 1 over 3n. So why did I end up writing this 1 and this 1? Well, because I want everybody to look like fractions, so I can look at all the denominators of the whole problem and decide what the LCD must be. In this case, the LCD for 1, 3n, 1, 3n again is literally just simply 3n. So I'm going to write my equal sign next to the main fraction and literally give each of the fractions this new LCD that I discovered. So let me write down the old fractions. Start with that. And next, give every single one of them the 3n. So keep in mind that when you write 3n, you're literally writing down 3n over 1. Okay, so you can write the 1 again, but you don't have to. So that's what we get so far. And the purpose of this is to multiply and reduce. So when you're done, there should be no fractions left over. So for instance, 3n times 3n divided by 1 times 1 will literally be 9n squared over 1, which is just 9n squared. Again, 1 over 3n multiplied by 3n over 1 is literally equal to 1. And there was a minus in the middle, so don't forget to write down the minus in the middle. Next, we do the 9n squared divided by 1 multiplied with the 3n over 1, which would give us 27n cubed. And then finally, there's the plus sign that we're going to copy and another 1. So the fraction is already simplified. However, this is a polynomial divided by a second polynomial. So now we want to try to factor as much as possible and reduce the expression to lowest terms. So for instance, 9n squared minus 1, that is literally the difference of squares. I can write it down as two sets of parentheses with 3n minus 1 and then 3n plus 1. Whereas 27n cubed is that SOAP formula. The bases are going to be 3n to the power of 3 and then 1 to the power of 3. So the bases are 3n and 1. So 3n and 1. Again, I square the first one, I get 9n squared. Square the 1, I get 1. And multiply the 3n with the 1, put it down the middle. And I'm using the SOAP business, so the plus sign, copies because it's the same, then opposite, then always positive. And why do we do this? We do this because now there's a 3n plus 1 on the denominator that matches with the 3n plus 1 on the numerator, so we can now reduce them and write down a simpler final answer. So it's 3n minus 1 divided by 9n squared minus 3n plus 1. That is the final answer. So although I didn't write this step earlier, you don't have to actually write it down to be able to factor the problem. But it is required that you factor and reduce the fractions, otherwise you will not get full credit. The systems or the graders will say that you missed something. So you can get partial credit but not full credit. Let's take a final look at this last one. So it's 1 plus x over x plus 4. All divided by the x on the denominator. So again, I'm going to add up this 1 and this 1 so that I can see that the denominators are 1, x plus 4, and 1 again. And I'm going to decide the LCD, in this case, is x plus 4. The 1 don't really matter. You can put them next to the x plus 4, but really it's the same as x plus 4. So you know what? I'm just going to get rid of the 1. So at this point, I'm going to give every single fraction that was there in the problem an extra x plus 4. So let me write down the original fractions that were written down. And here they are. Next, I'm going to give each one of them an extra x plus 4. Remember, the same as x plus 4 over 1. So you can go ahead and give this one an x plus 4, which is the same thing as x plus 4 over 1. And let me put parentheses around everything. And finally, the same thing on the last one, x plus 4. And you can also give it a 1 underneath. So I don't like how this is written down right now because it's not very well notation. So I'm going to go ahead and extend the fraction. At this point, we can reduce whatever we can. So in this first fraction, nothing reduces. We just end up with x plus 4 times 1 divided by 1 times 1. It doesn't matter, just x plus 4. Then we have the plus sign, which I'm going to write in the middle. The second fraction, I can reduce the x plus 4 and the x plus 4. And when I reduce them, I just get 1 and 1. So x times 1 is x, divided by 1 is just going to be x at the end. All divided by x times x plus 4. In this case, I'm going to leave it as x times x plus 4. This is a rule of thumb in this class. We, typically speaking, don't want to FOIL the denominator. So if it's already factored like it is right now, that's actually a good thing. We want to leave it like that. However, the numerators, we have now x plus 4 plus x. So it seems like the x and the x are actually like terms. They both have the same variable. So what we're going to do is add them up. So keep in mind that x plus x is literally 2x. Why is that? That's because the first x has an invisible 1. The second x has an invisible 1 as well. So when we add the terms, we just add the 1 plus the 1 to get the 2 at the end. So this gives us 2x plus 4, all divided by x times x plus 4. Now, can I reduce the fraction to lowest terms? The answer is no. In order to reduce it, the terms have to match exactly identically to be able to be canceled out. So I cannot cancel this x plus 4 with this x plus 4 because it's really not x plus 4. It's actually 2x plus 4. Now, even if you try to factor this, even if you try to put 2 on the outside, the GCF with x plus 2 on the inside, all divided by x times x plus 4, it still will not reduce because nothing matches 100% on the numerator with the denominator. So which one is the right answer? Well, this one is the right answer, and also this one is the right answer. They're both good because nothing really can be reduced.